What if the garments changed according to the weather or the user's activity? Or if the pipes could be repaired automatically if they crack or break? Auto-assembly furniture, growth adaptive prosthesis. These are just a few of the potential uses that 4D printing technology is expected to have. In this video, we'll explain how 4D will transform the manufacturing industry. But first, please like, subscribe to TechStar, and then sit back and relax. Despite ongoing research, the discovery of new materials, and uses for 3D printing, which has been around for about 30 years, new technologies like 4D have arisen. They have created a project, of which 4D printing is a part, at the MIT Self-Assembly Lab. Its mission is to reinvent building, manufacturing, product assembly, and performance by fusing technology and design to create self-assembly and programmable material technologies. For its part, a study by the Harvard University Wyss Institute has been able to print a substance that, when it comes into touch with water, alters its shape and sprouts flowers at its ends. To do this, they created a material inspired by organic forms, like those found in plants, and printed cellulose fibers into it. What does 4D printing mean? In 4D printing, which is based on the self-assembly concept, a 3D printed object is changed into a different structure under the impact of outside energy inputs like temperature, light, or other environmental stimuli. That is, creating an object using 3D technology that, due to the characteristics of the material used to create it, can change when exposed to environmental stimuli. The capability of objects to change over time without human intervention is precisely what distinguishes 4D technology from 3D technology. What kinds of materials are used? The technology of 4D printing, which is based on standard 3D printers, is not as important as the materials. The materials available are not as diverse as those used for traditional 3D printing. Because this technology is still relatively new, there are, however, a few that are very fascinating. SMPs, shape memory polymers. Polymers known as SMPs, shape memory polymers, are hard at room temperature and exhibit unique characteristics as they reach the glass transition point. Convena's SMP TPU, for instance, is a 4D filament with a TPU-based composition that enables post-processing to change the geometry of 3D printed components. The objects printed with this filament can be manually altered to take on a different shape and preserve it over time due to its unique composition and shape memory polymer technology. A 3D printed component made with TPU SMP filament can have its shape changed by putting it in a container of hot water until it reaches the glass transition temperature. The object softens at that point, allowing the user to readily change its shape. When the piece is cooled, it keeps its acquired shape and is still stable. Additionally, by reversing the procedure used, 3D printed TPU SMP pieces can regain their original shape, specifically re-achieving the material's glass transition temperature. LCE, liquid crystal elastomers. LCE has heat-sensitive liquid crystals in them. The desired shape can be programmed by manipulating the orientation of the material, which will relax and change following the instructions when the temperature changes. Hydrogels. Water-based polymer chains are mostly employed in photopolymerization procedures to generate long polymer chains. Due to their biocompatibility, the latter is concentrated in the medical industry. Furthermore, certain 4D printing techniques may incorporate several materials, primarily substances like wood or carbon that are added to SMP or hydrogels. In this manner, things with mobile and stiff areas are created. Applications. Given all the benefits that these intelligent materials provide us, 4D printing has a wide range of applications. Let's now examine a few of them. Building. Building climatically appropriate structures like bridges, shelters, or other facilities would be a significant advancement in this area. The interior conditions could be altered and enhanced thanks to 4D bricks that can change walls and ceilings to adapt to the environment. Medicine. In this situation, 4D printing opens the door to the creation of customized, intelligent, and developing gadgets. For instance, manufacturing a 4D implant would make it easier to monitor its status and viability after it has been inserted into the patient. This idea is relevant to the creation of cellular structures as well as regenerative medicine. Using 4D printing will enable cells to adjust to the human body based on factors like temperature. When referring to medications, it would be conceivable, for instance, to print a device that releases the required dose based on the patient's body temperature. Transportation. B&W and MIT unveiled their inflatable material, which adapts to air pulses by changing its shape and size a few months ago. The possibilities are quite intriguing since, in the future, we might have tires that can fix punctures on their own or adjust to the terrain and the weather outside. In the instance of the aircraft sector, a 4D printed component might modify its function in response to variations in temperature or atmospheric pressure, as these parts could replace hinges and hydraulic actuators, greatly lightening the devices. Airbus is now working on these improvements. To cool its aircraft engines, it is also working on the development of materials that respond to heat. NASA has developed a smart cloth that was 4D printed. The metallic mesh, which is made up of connected silver parts, has heat regulation printed into it. That is, both the form and the purpose of the contents have been printed. It might be the perfect material to use for creating astronaut suits or coating spacecraft, since it can reflect heat from the outside and keep it inside. Fashion. 4D printing is used in the textile business as well. One option is the ability to print shoes that adjust to movement, impact, temperature, and atmospheric pressure. The United States Army has already entered this field and is testing uniforms that alter color based on the surroundings, or that control sweat based on the soldier's heart rate or the surrounding temperature. 4D technology will undoubtedly transform manufacturing and the nature of items in the future years, much as 3D printing did at the time. Even though it is still in its infancy, one new phrase is already entering our lexicon as we work to comprehend the potential and boundaries of additive manufacturing and 3D printing. Just 3D printing with the addition of a fourth dimension, or 4D printing, is a new digital manufacturing technology. As a result of its inherent qualities that react to external cues, the printed material will be able to modify, transform, or move independently once it is complete. Although the technology is still relatively new, it is anticipated to be employed in a wide range of industries, including those related to building, infrastructure, the automotive and aerospace industries, and even healthcare when combined with bioprinting. Materials used in 4D printing directly affect the final product. The so-called intelligent materials are solids with a feature that entirely results from internal material characteristics and changes in reaction to an external stimulus, such as heat, light, moisture, pressure, or magnet. The three-dimensional world of today is constructed of passive inert elements like glass, steel, and masonry. Intelligent, dynamic, and animated elements that move randomly make up four-dimensional structures. Additionally, it can be mixed with passive materials and exhibits autonomous properties in response to a stimulus, such as swelling, contracting, or bending. They can now move and transform without the use of robotics, electronics, or motors thanks to this. Consider the pineapple as an example of a clever natural substance. The cone can be opened or closed by two layers of strong fibers that run in different directions, allowing the seeds to be released only when the conditions are suitable for their germination in the soil. The cone closes up to shield the seeds from extreme humidity. Materials engineers are driven to comprehend and imitate the intricate mechanisms of adaptability, resilience, and efficiency in nature. It is also the driving force behind biomimicry, in which 4D printing can realize a lot of concepts that technology has yet to accomplish. The ability to program the material so that it responds under environmental circumstances is the primary goal of 4D printing. But what use could all of this be? There are some ongoing studies in which heated or agitated objects bend and assume a different three-dimensional volume. Consider a drainage pipe that may change size in response to the water flow, or a sewage system that can transfer waste over hills by contracting and relaxing in a manner akin to the peristaltic movements of the colon. An in-depth study is also being done on the use of polymeric materials printed in 4D for bone restoration or tissue and organ regeneration. There are a lot of options, and experimenting can go quite far. Imagine the benefits that smart materials and 4D printing could provide for building envelopes, allowing them to respond to a wide range of stimuli and climate changes. Although the technology is still in its infancy and is centered in a small number of facilities worldwide, a bright future is in view. The outcomes are frequently astounding when we try to comprehend and mimic nature rather than try to control it. If you enjoyed this video, don't forget to hit like, the subscription button, and the notification bell. To get notified when new videos are uploaded from this channel, please share your thoughts about the 4D printing trends that'll revolutionize the way we manufacture in the comment section below. Thank you.